So good evening, welcome back to Plan 252, transport modeling. Okay, so today this is our agenda. So today you will learn about the chemistry of transport policy. Okay, so you can go to revolutionized model and find the slide there. Okay, there is also a link to go to the lab, about the chemistry of transport policy. And then there is also assignment later, okay, for you to learn about it further. Okay. So next week we will have a midterm exam. Okay. From I will open the exam because this is online exam. So I will open the exam from 6 a.m. okay, until 6 p.m. on Friday. Okay. And these are the coverage. So these are the topics that we have discussed. So from urban planning, land use activity, transportation interaction. We also discussed last time about is modeling, okay, and then regression, traffic flow theory, okay, NFI, the network flow identity, network representation, and then how to compute the FN manually. And this one is basically the lab, ideal traffic design. So, and this is today. Right. So my question to you, do you want to have the class after that? Because last week we don't have meeting. Or you want the entirely for midterm exam? Both. So what do you think? Any opinion? So is it okay we have class after that or not?
You can have cluster
Hmm?
if everybody wants have a class on.
Yeah, exactly. That's if anyone said, "Oh, I cannot because I work and so on," so then I can extend the midterm until 9. That means we don't have class. But
Sir, I think it's better if, because I have to work in the morning, so maybe we can extend it until the class time.
okay, yeah, this is until 6 p.m. From morning 6 a.m. until 6 p.m. But
Okay. So if we won't have class, the exam won't be extended as well.
until 9, yes.
Uh, yeah, I think I prefer, for me personally, I think I prefer that, sir.
Until 9. So you
Yeah,
want until 9. Okay. So in that case, we don't have class next week. So only entirely for midterm.
yes, sir.
Thanks, sir.
That's okay. Yeah. So I can speed up the following weeks in that case. Okay. So uh no. Okay. So this one we put it until 9. So no class. Okay, so with that decision, so let's start with our topic for today. Okay. Can you go to Moodle? So if you go to Moodle, I don't know, Zoom. Exactly. Okay, so you will see this the lab. Okay, and these are the top slide for today. And these are the assignment. Yeah. So the assignment is individual. And it's the purpose so that you can practice more. Are you ready? You have the material, okay? Okay, so let's start. Okay, so I call this the chemistry of transport policy. Okay, so this is similar to the analogy to the chemistry. You learned chemistry before, right? When was that in high school? Yeah. So you learn about atoms, you learn about molecule, right? So you can combine the atoms with other atoms, and then you can create molecules. That's similar. Okay, but we will apply this analogy for transport planning. Okay, so you will create a language for transport planning. Okay, so this is a formal language designed so that you can make the planning to be more precise, okay, more transparent, so that you can audit the plan. Okay, so these are the overview. Okay, there are 6 modules. Okay, we will discuss today. So about 140 and 138 slides. So quite a lot. Okay. So we'll discuss about the motivation, why we need this chemistry of transport policy. Okay, what is the vision and the principles, and then slowly I will give you the building blocks. Okay, the atoms. Okay, from here we can create similar to chemistry. We have periodic table of the atomic policy. Okay, and then you can compose. You can start to compose the atomic policies into molecule and apply some logical operator. And then we go more advanced concept and formalism, okay, with the logic. Yeah. At the end, I will introduce the EBNF. Okay, this is the formal language, just short. Okay, and then we will have a lot of practices. Okay, and option. Is that okay? So, okay, let's see the big picture first. Yeah, we have learned about NFI and ideal traffic assignment, right? Last time. Okay, so you have the network flow identity. Okay, that is very useful to think strategically what kind of policy in the macro level. Yeah, I hope you still remember. Okay, and then we also have the ideal traffic assignment. So you have the matrices, and then you can put to compute the travel time, the delay, the flow, congestion, and so on. So chemistry of transport policy is in the middle, in the tactical level. Okay. In the operational, of course, you will have the sensor, the sensing device. This is practically not your part. Okay, these are the job of electronics and engineers, basically, or control engineer, that they are doing what is called intelligent transport system, ITS. Okay, so these are mostly related to electrical and electronics. Yeah. So the ITS. Now, let's go to the first part. Yeah. So anytime you want to have any questions, so you just raise your hand. We can discuss more detail. Yeah. Okay. So the problem with the traditional planning, okay, urban planning, okay. So historically, it has been shaped by more powerful narrative, isn't it? Authority of the urban planner. Okay. Is driven by intuition, okay, and the politics, okay, not reproducible by science, meaning that it has a lot of ambiguity. Okay, how can you sure that your policy that you plan actually work? Okay, how are you going to learn from the past mistake if the input or the logic is actually clear or not? So this is ambiguity. Yeah, so there is a lack of formal structure. Okay, means we often cannot reproduce what the other urban planners are doing. you cannot even test the policy. Okay, and then after you implement, it's a big challenge because basically you talk about average, right? Average travel time, which you don't have the sensor for all the links in the network. So in this case, very difficult to say that the urban planning itself is actually successful or not. So we practically need a system that is transparent, okay, and hold us accountable for our own prediction, isn't it? Okay, so what often happen is actually the politician, okay, or the urban planner, okay, leads to experimenting in public. Yeah, you test directly in public, or maybe it will work. That is hypothesis only, right? Whether it will work or not, you don't know, because your plan is like 5 years, 10 years, maybe 30 years. How can you know, right? So let's see the core problem we are trying to solve. Yeah, historically, transport planning has been more art than science, isn't it? So these are the problem of ambiguity, yeah, because the policy language remain open for interpretation. Yeah, you cannot reproduce again. So in that case, you cannot test. Okay, so because of this, okay, we want to have a better way of planning. Okay, so we want to have better transparency, we want to have better accountability, and the planning can be repeatable and then can be shared all over the world. Okay, this is why we need this kind of language of chemistry of transport policy. Yeah, so the chemistry of transport policy will redefine the plan. Yeah, because it will become repeatable, objective. Okay, and you can use AI. Yeah, in fact, the lab there will help you to create the prompt for AI. Yeah, so think about it as writing computer program as your policy. Yeah, in this case, the language will be unambiguous. Yeah, exactly one thing. Yeah, and then it will be composable. So we can build the complex strategy from very simple atom. Okay. Next, you will understand its part later on. Okay. And then most importantly, you can test. Yeah. Auditable. This is what you will do in your group project. Yeah, as your practice. Yeah. Also for the assignment. Yeah. So then we can trace the logic. Yeah. Every decision that you make, you can simulate. Okay. What will be the effect? Okay. Before actually touch the streets. Okay. So this will shift the planning from belief-based to evidence-based. Yeah, because you can simulate before implementation. Yeah. Beyond that, actually, we can also do optimization and so on. That's in the future. Yeah. So to make this more intuitive, okay, we use a powerful analogy from chemistry. Yeah. Why? Because in chemistry, we have similar hierarchy. Yeah, we have the atoms like hydrogen or carbon or oxygen, like that. Yeah, in our language we have also policy atom. Yeah, later I will introduce you. So these are the example of policy atoms. For example, add capacity, remove links. Yeah, so I will introduce you later with the atoms. Don't worry. Yeah, and then these are the smallest possible action that you can think of. Okay. And then next, you can combine these atoms, okay, into molecule. Okay. When you combine this into molecule, it will become complete coherent policy. Okay. For example, yeah, you want to reduce capacity for cars only, and then you want to add capacity for bus, right? So say you remove one lane for car and you replace that one lane for bus. So then you will put this way, yeah, reduce the capacity in the road X, yeah, X is something, and then for cars, and then you add that capacity for the bus. So this is very clear what you are going to do, okay, and repeatable. Say, for example, you can create the same policy in Metro Manila, you can put it in Cebu, all right? And then once you have this molecular policy, you can simulate this effect in the ideal traffic assignment, yeah, or any transport model, yeah, in the transport network. So the reaction part of this chemistry represent the simulation, okay, of this policy, and then you can compare which one is actually the best. Okay. Is this clear? The idea of analogy, okay, of traffic chemistry. Yeah. So this is the agenda for today. This is the course objective for today. So you will understand why, yeah, we need the formal policy language, right? We just discussed. So, and then we will define more detail, okay, what is the atom, the basic unit of any policy. Okay, and then you will practice, yeah, how to compose these atoms into a complete strategy. Yeah, and eventually you will have hands-on with the virtual lab. Yeah, I have built that several versions actually. Yeah, so then you can validate your own policy whether it's correct or not. Yeah, so I hope by this end of the class today, you will not just understand the theory, but you can also apply this into practice. Okay. So let's go with the atoms. These are the atoms that I discovered. Yeah, but you can probably discover something else later on. So where did I come from? Yeah, I come from the network. Okay, in the network you have node and links, right? In the links you have capacity. So then the smallest, yeah, policy that you can do is actually add capacity, say add one lane. Reduce capacity, that means reducing the number of lanes. Okay, add links, that means you add a new road, right? Remove link, that means you remove that road, that links, yeah, from the network, probably for something, for other reason. Yeah, whether this is temporary or not. Yeah, and look at the symbol here. Okay, C mean capacity, right? A mean adjacency matrix. Yeah, V here is the node, meaning the vertex. Yeah, U is the maximum speed. Yeah. S here is the stochastic matrix in ideal traffic assignment. You remember? Okay. And kappa here represent the demand. Yeah. The same as in NFI last time. Yeah. Network flow identity. Yeah. And then if you look at the symbol delta here represent the change. Yeah. The same thing, we have also delta in the smaller letter. Yeah. Delta like this. This represent also the change, but in temporary. Is it clear or not? Okay. So these are the atoms. Yeah. So the first core principle of our language is atomicity. Yeah. Just like all matters made of atoms, okay, all transport policy can be broken down into very fundamental, yeah, irreducible atoms. These are very critical rule. Yeah. You cannot create new atoms, yeah, but you can create molecule based on the atoms. For example, you cannot activate Ramitz rings. Yeah, this is not atom, this is molecule. Okay. So then RAM metering means temporary you reduce the capacity in the RAM, right? So then you need to translate the everyday jargon into the atomic level. Is that clear? Okay. So what is it doing? Yeah, because this is temporary reducing the capacity of the RAM, so we express it as temporary reduce the capacity. Yeah. So by this principle, you will force yourself, okay, to be absolute clarity. Yeah, remove some ambiguity. What is your policy definition? Yeah? So basically, this is the analysis part. Yeah, you break down the one that you want into a smaller part. Yeah, analysis. Clear? So second, this is synthesis. Yeah. So after analysis is breaking down, so now you synthesize. Yeah. You compose. Yeah. If atomicity represents deconstruction, okay, our second principle, composability, means construction. Yeah. So take our example, simple example, fundamental atoms, and then assemble them into more complex structure. Yeah. When you combine, these are the operator. Yeah. Union mean and, yeah, and arrow means sequence. This mean tilde mean not. So this is a logical operator. Okay. So far we can use only 3 operators. Yeah. And then there is one more operator identical like this. 3 bar mean identical. This is how you define the name. So you can define the molecule, you can define the name of place, for example. Say you want to define the link, yeah, from the OSM or Google Map, there are a lot of nodes, isn't it? Right? So then you define this is ETSA. So then ETSA, okay, using this atom, and then you put the bar, what are the nodes number? Okay, this is so you define it very precisely, then other people can actually take your node, yeah, of the molecule or definition, then they can also apply. So you can be tested. Is it clear or not? Yeah. So this will allow us to build policies in a modular way, right? So we can define simple policy, okay, and then we can keep name, yeah. So like base metering, yeah. Base metering mean temporary reduce the capacity for all RAM, for example. Yeah. Then you can reuse, yeah. You can reuse the same name here to combine. So atom can be combined with other atoms to create molecule. Molecule can be combined with other molecule or atoms to create higher level molecule. So you can compound very complex molecule policy. Okay, this is an example. Yeah. So the third principle is, this is the most important, reproducibility. Yeah, this is where the scientific method going into planning. Yeah, why? Because every policy now written in precise formal language. Yeah, then you can save, you can share, you can rerun, yeah, by anybody who has the same technique. Yeah, so it is no longer black box, right? So now become white box, mean a glass box. Yeah, mean the policy that developed in one city can also be tested in a model for another. So you can share. Nice, right? So it means the result can be also independently verified. Yeah, will create a very powerful feedback system, yeah, feedback loop. Okay, so that we can rigorously compare our prediction with the reality. Yeah. So this is actually the cornerstone of scientific or engineering discipline, right? So we ensure that our work is actually transparent, yeah, and justifiable. This is the true learning. Yeah? You can, when you say, oh, I predict here, how can your prediction be true if there is no documentation, right? Even if you just make it into report, there is no learning experience. But once you put it very clear, okay, so we can actually verify your prediction. Yeah. Say in this drawing, yeah. So say the same in Asian office, yeah, PRT system, for example, can be also adopted in Europe, for example. Yeah. So this is very nice because it will trigger a lot of knowledge sharing, yeah, among the planners all over the world. Okay. And most importantly, it's not just technical, but it's also ethical. Yeah. So the chemistry of transport policy, yeah, will cultivate better planning practice. Yeah. So will show honesty in your assumption, yeah, transparent input. Okay. So you open your assumption, and it will promote objectivity, isn't it? By ensuring the model evaluate the policies based on the logic, yeah, not just persuasion or rhetoric. Yeah. And then it will foster responsibility. Yeah. So what is our prediction? Yeah. Can be fully reproducible or not? Can be scrutinized. Okay. And finally, it encourages adaptability. Yeah? If there is some mistake, then we can learn from our mistake, isn't it? So this is actually about building trust through transparency and accountability. Yeah, you can protest against the corrupt official, but it should start from yourself, isn't it? If you yourself not transparent about your own planning, so how can you blame other people, right? So let's start from us, okay? From our own discipline, that we need to have transparent, we need to have honesty, okay? So that's why this language is very important. I hope this encourages you. Yeah, the motivation is very important. Now let's go to the quick tour. Yeah, with our workspace. There is an IFN virtual lab, so you can go to that chemistry of transport policy. Go to the lab there in the Moodle. Okay, then you will see this kind of simple web page. Okay, so this is where the theory we discuss will become practice. Yeah, so everything you need is just one interface, right? So if you go in the before, it will go to ideal traffic assignment. The next part is the IFN transport. So this is in the middle. Okay, so we are going to walk through the few key areas, yeah, of the lab, yeah, so that you know exactly where to find everything, okay, when we begin our exercise later. Is that okay? Okay. So in here, you will learn about the policy language. Okay? There is a scenario example here. So if you are not sure, you just scan this QR code so you can go using the mobile phone. Yeah. And then if you click this scenario example, you will have a lot of example there. Okay. So a lot of examples. And once you have that, so when you click one of them, okay, you will have the policy canvas. Yeah. This is not editable. So to edit, you will go to the validator. Okay. in this policy canvas, you will see this is the molecule or the atoms. Okay, so you can copy and paste this to clipboard and then paste it in a text file, or you can click this send to validator. Yeah, it will open this policy validator. Okay, and then in this policy canvas, you will have the name, you have the symbol, either in the simplified version or the formal version. Okay. Yeah. In the policy validator, this is the policy canvas. Yeah. So the policy canvas, this is the main workbench. So you can add your atoms operator. Okay. Then you will see the formal policy strings here. These are examples. Can you see the semicolons? Okay, to separate one items compared to the next. Yeah, so this is how you will read. Is it clear? Okay, so as you will add later the atoms and the operator, yeah, you will see your formal policy strings appear in this box. Okay, and then below here you will have the plain language interpretation. Yeah, so you can click the symbol or you can click back the name, so that you can see the difference. Yeah. If you put formal, it's always in symbol. Okay, so say you go to the validator, you put your own policy, and then you send back to the policy canvas so that you can see the interpretation. So you can click this interpret. Yeah. Or you can modify using delete the last part. Yeah. So this is incredibly useful. Yeah. For checking. Yeah. Whether your policy is written in the one that you intended to write or not. Yeah. Okay. So notice that there is a toggle. Yeah. You can see in different notation. Okay. The next one is policy validator. Yeah, below you can see the policy validator. Yeah, the top is policy canvas. So you will see if you click this arrow, you can open that. Yeah, or you can send to validator. You can open this. Yeah, this is where you can type actually. Yeah. Okay. So you can type here. Yeah, and then you can validate. And you click this to validate. Yeah, or you can parse. Okay, and then you can send back to the policy canvas to interpret. Okay, so this is your spell checker, grammar checker of the policy language. So you can type, you can paste any policy string here. Okay, it will tell you if this is syntactically valid or not. Yeah, before you try to simulate or to run the policy. Yeah, so you should always check it here first. Yeah, of course, valid policy is a first step to successful simulation, isn't it? Because the same language will be shared for all. Yeah, so you can have guarantee that other people that learn about this will also have the same meaning. Okay. Next is the parser. Yeah. So while the validator give you simple yes or no, right? Green, yeah, or red, okay, in your syntax. Yeah. So the parser will give you why, yeah, and how. This is our diagnostic tool. Yeah. You can feed it policy strings, okay, and then it will show you the blueprint. Yeah, this is, for example, node avenues are the nodes. Yeah, and then what are the molecule? Yeah, in the molecule you will see the action. So coefficient represent the number of lanes, right? what are the location, and then what are the modes, okay, what is the time, and so on. So this is incredibly useful when you are writing a very complex and multi-line policies, okay? So you need to make sure that the logical structure is exactly what you intended, isn't it? So you can think this like your X-ray, yeah, for your policy, yeah? So you can see the skeleton of what is inside, yeah, debugging your complex policy, okay? Next is the AI prompt generator. Yeah. So this is just a prompt that you put what policy you want. For example, oh, I want to close the road in South Avenue from this and that. Okay. And then when you click the AI prompt, okay, it will open a new page, right? And then it will give you the prompt that you can fit into the AI. Yeah, this is fantastic learning tool, isn't it? So yes, many of us know what we want the policy to do, but we may not know the exact syntax to write it, isn't it? So this is the tool to bridge that gap. Yeah. So you describe your goal in plain English, okay, and then the generator will take your description and wrap it into the set of expert level instruction for the AI. So it's essential to tell the AI you are the transport expert. Yeah? Now you need to follow exactly this rule. Here are the grammar that you need to use, and this is what you want to get, yeah, from here. You can try, okay, and post it to any AI that you want. So I tried this in GPT, yeah, and in Chichi, in Copilot, and so on. So, and it will give you the exact policy. Yeah. Of course, some AI are not really good enough, so they may produce wrong results. So that's why you need to learn about this today. Yeah, it's not just about the AI. Yeah, so they sometimes give you wrong result, either wrong syntax, wrong symbol, or semantically wrong. Yeah, so you still need to think. Yeah. AI can help you, but doesn't mean they are everything for you. Okay? So I hope this is useful. Yeah. Yeah. It will give you something like this. Yeah. These are the example of prompts that you have. Yeah. So, and then when you put, it will give you the actual, so you click, yeah, copy to clipboard, it will copy to your clipboard, and then you just paste it in your AI. Nice. Okay. And we have extensive documentation there. Yeah. So actually, this slide based on this documentation. Yeah. So how to use this lab. Okay. And you don't need to look into separate manual. So everything is in here. So this is full user guide, complete list. Yeah. Of all the valid atom, the rule, the operator, even deep level formal grammar. So this is your reference. Okay. Now you are familiar already with the lab in quick tour. Let's dive into the detail, yeah, of the atom themselves. Yeah. So in this documentation, you can click more detail, more detail. Okay. So it will give you the even the formal grammar there. Yeah. Okay. So did you try? Is it clear? Yeah. A lot, I understand, but imagine you just learn, but how about the one that actually built this? Yeah, take a lot of time, more than Okay, so it takes several years to make this. Yeah, just one page that we discuss in just 3 hours. Yeah. So let's go to the module 2, second part. We have 6 parts, right? So here we get into the practical details about our language, which is the most fundamental component, which is the atoms. Okay. So let's discuss first about the definition of what is policy, right? Okay. You always say policy and so on. So in IFN transport, or ideal traffic assignment, policy is very clear. Definition by mathematics. Okay. So you have adjacency matrix, right, as input. You have capacity matrix. You have the, what is this? Maximum speed, free flow speed, U. And you have also the L. What is L? L is the distance, the link distance matrix. So these are the input. That arrow here means the capacity matrix must have the same network structure as adjacent matrix. If you put the 0 and 1 of these three, C, U, and L, must be exactly the same as A. So that means if you add the links or remove the link, that represent the adjacency matrix that you change. And then from the C, using Markov split, you can have the stochastic matrix. Okay. Then again, these are the input. So 1, 2, 3, 4, 5. And then to get the ideal flow F, okay, you need to have kappa. I did not put here. The kappa is the demand, the total demand in the network. The scaling. Okay. So these are the input. And then from there, the capacity and the flow, you can get the congestion. Now these are the output, isn't it? The congestion, the speed, the travel time, the delay. These are the output. The process is the flow. But the input are this part. This is the part of input. Well, so now knowing the input, then you can now define what is policy. Policy means the change in the input. Clear? So policy, so let's put it P, mean the change in the structural network input. Okay, so using IFN transport, you can download from OSM, you get the baseline, isn't it? Easy to get the baseline, It's automatic practically, But to create the alternative scenario, what you will do? Now you need this chemistry, So you need to define clearly what you want to change in very detail. You want to change in the adjacency matrix or in the length or in the speed or in the capacity, the number of lane or the road width or the total demand or change in the traffic signal. So that means you need to change the stochastic matrix. Right. So, or you change the demand. Okay, for example, you have congestion, so you put the cost and changing the cost. That means changing the demand, isn't it? Okay. So based on this, you will see now policy is defined very clearly, okay? Because mathematically you can even put there, okay? Then you can define the alternative scenario very detailed, okay? I changed from the baseline scenario, these are the chains to get the new alternative scenario N1. Clear, Okay, so You see, this N0 is a baseline. Okay, you add with the policy, then you create an alternative scenario. Clear? Yeah. So when we say transport policy, yeah, you change from the baseline, okay, whatever change you want, but not all change, yeah, all the change that you can translate back, yeah, into this input, isn't it? Structural input. Okay. So what is atom? Atom is the smallest unit of change, yeah, atomic policy. Okay. So think of it like the gear in the complex machine. Okay. It just perform one and only one function. Yeah. For example, you can add capacity. You can remove the link. Yeah, you can change the demand. But you cannot break it down any further than that, isn't it? So it's every policy that you write, okay, no matter how ambiguous it is, so you will build from this simple, very powerful building blocks. Yeah, these are the example of table, okay, and these are the application scenario that I have. For example, you want to have either temporary or permanent change. Okay, you want to add the lane, so capacity, right? Or you want to add the width, for example. Again, this is capacity. Yeah. Maybe you want to add the road. Say you want to build the bridge. Yeah. Whether permanent or temporary. Yeah. This means you add the link, isn't it? Okay. Or you want to reverse the direction and so on. Yeah. These are the example of scenarios. Yeah. These are the description, okay, of the policy that you want. Yeah. Eventually, you need to bring all of this into the atomic policy. Yeah. These are the table of atomic policies. Yeah. This is not exhaustive, but the majority you will use this anyway. Yeah. So remember, policy represent the change in the network model. Yeah. So atoms represent the action, the verb, yeah, of the policy language. Yeah. What kind of change? Okay. So then every component of this very complex policy that you will create need to break down until the atoms. Why? So that you can actually input this into the computer, yeah, to simulate. Clear? Yeah. So let's go to the anatomy, yeah, the formal grammar of atom. Yeah. There is a very strict formal syntax. Yeah. Why? So that it is ensure that this is the machine can read this, yeah, like a program. Yeah. So the syntax is you have the coefficient, yeah, with the bracket means optional. Okay, so this is optional. The required is only action and the location. Yeah. Only in one atom, you need to have action and then you need to have location where, yeah, this action will be applied. And then you can have mode as optional. Yeah, what specific mode that will be affected by this action. Okay, and then you will have time. Okay, the time window when this action will be applied. Yeah, again, these are optional. Yeah, the time is optional. Okay, let's apply this structure into example. Okay, so this is the example. So this is the atom represent the policy to reduce the road space for the car, okay, in the South Avenue during the morning rush hour. Yeah, as you can see here, yeah, each piece of this syntax have very clear meaning. Yeah, two here represent the our coefficient, that means 2 lane, right? And then the temporary reduced capacity. Yeah, this is the temporary reduced capacity is the action. Yeah, and South Avenue represent the target. Yeah, location. Okay, and then car is the affected mode of transport for this policy, and then the R, and then 7 to 9. This is the time. Now this is a specific morning peak that we want. Yeah. So when we put this together, okay, this is the component form complete, precise, verifiable policy instruction, isn't it? Yeah. So let's focus first now in the action. Yeah. So in the language of atomic policy, you have action. Okay. Action is the verb of our policy sentence, isn't it? So this language provides the fixed, finite set of possible action. Okay. And then they fall into logical categories. Yeah. So I put this into category 1 to 5. Okay. This is the action that change the control group, yeah, of the links, or adding capacity, yeah, or optimizing the signal, yeah, S. Yeah. And we have this action to change the actual physical network input in the ideal traffic assignment. Yeah. So, and we have this action that change also the travel demand. Yeah. So, yeah. Later we will go much deeper than this. Yeah. At least I want to introduce you step by step. Okay. So when you change the physical characteristic of the links, that will change the distance, will change the maximum speed, yeah, or the free flow speed. Yeah. You can also change the capacity. Yeah. If you would change the direction of the links, then you need to change the adjacency matrix, isn't it? A is the adjacency matrix. Yeah. So if you want to change the node existence or certain probability distribution, that means, for example, the traffic signal timing, that means you need to change the stochastic matrix, yeah, or the adjacency matrix. Again, if you alter the total demand of the network, then kappa, yeah, is the one that you change. Yeah, remember, yeah, policy represents the change. Okay. Next, yeah, in the atomic, you have action, then you have the target. The target consists of two, yeah, location and then the mode. Yeah. So that if the action represents the verb, okay, now the target represents the noun of our policy. Yeah. This tells us where the action will happen. Okay. So the location is mandatory, is required. Must be precise. It's not just main street, but you need to specific segment of the main street that have unique IDs. Yeah. In your model, isn't it? So by doing so, it is ensuring that the target exact piece of infrastructure that you intend to change is clear. Okay, so the mode is optional, but it's actually incredibly powerful. Yeah, it allows us to apply a policy only to cars, only to bus, only to pedestrian, only to bike, and so on, yeah, or freight transport and so on. So this is crucial for designing equitable policy that can prioritize public transit, for example, or active mobility, yeah, without affecting other traffic. Yeah. So if you omit this, so this is optional, right? Meaning that you don't have mode, that means it applies to all modes in that location by default. Okay. So clear, yeah? The action represent the verb, the target represent the noun, yeah? Now, if you combine that, okay, now we have these are the one that you probably will use. This is the policy periodic table. So these atoms, we group them. What do you want to do? You want this is the group, the one that we put 1, 2, 3, 4, 5 here. Can you see? So group 1 to 5. Okay, so anyway, it's clear here. So L mean the length, and U represent the maximum speed. C the capacity matrix, A represent the adjacency matrix. S or A represent the adjacency matrix and the stochastic matrix, and then kappa represent the demand. So you can either add or reduce, or you can modify. Either permanent or temporary. A is permanent, B is temporary. This is in the symbol. And this is with the name. The name we try to make it standard name. Okay. So think of this atomic action as a periodic table of policy elements. So you cannot invent a new one. Okay. How about the dot? So the dot means unclear yet. So similar to Mendeleev chemical periodic table, with their properties, by grouping these atom or policy atoms by their function, I hope it will give us a mental map, about the tool that we have. So broadly, we have the atoms that affect the control input, the width of the road, traffic signal timing, and so on. So, and then we have the atom that change the physical structure of the network. So building the new road and so on. And then we have also atom that change the demand. For example, congestion pricing, the increase of the costs and so on. So, and then you can also see that these are divided into permanent and temporary policy. Anyway, we will spend the next few slides diving into more detail into a few of these categories in the few examples. So no worries. Okay. So this is an example of adding capacity. Add cap mean adding capacity, and you see delta mean capital delta mean permanent, C mean capacity, plus mean add, right? So if you increase the capacity of a link, say before 2 lanes now become 3 lanes or something. So this is straightforward, isn't it? You just want to increase the capacity in the network. So this is the example, add caps in the road. So this permanently increase the traffic carrying capacity in that segment of the road. Another example, lane widening. You want to build a new bus platform, okay, or you want to add protected bike lanes. So these are the atomic policy that you will put. Okay, so the simplest is just the action and then the location. Clear? This is an example. So before bus lane project. So before is for general traffic. Okay, now you add capacity for bus. So you add capacity for the new mode with this bus. So if you actually use the same traffic, so then you need to reduce. So you need to combine into molecule that you reduce. Union, okay, reduce capacity in the same for car, for other vehicle than bus. Okay, so can you notice the use of optional mode parameter here? The bus. This is mean the new capacity is added exclusively for bus. Yeah, very precise. Okay, so now the counterpart of adding capacity, of course, reduce capacity, isn't it? So in this case, you will see delta mean change, yeah. C mean capacity minus, so reduce the capacity, yeah. So delta C minus, okay, this atom reduce the capacity, yeah. It will use in the intervention, for example, lane closure for construction, for example, temporary, yeah, or a deliberate road diet, yeah, to calm the traffic or to restrict certain bridges, yeah, because it can no longer support the original load and so on. Yeah, so you reduce the capacity in the road bridge, old bridge. Yeah. Or you want to use this lane for a bike or for maybe pedestrian, yeah, or the green space, yeah, for public park possible. Yeah. So this is the atom, yeah, reduce capacity, right now. Okay. So this is the example. So road diet. Yeah. This is the core of this the core of this policy is actually reduce the space for cars. Yeah. So we can model this with reduced capacity. Yeah. Here we have example 2. Yeah. If you put 2 red cup, that means you remove 2 lanes. Yeah. Okay. So the coefficient you can also put. Yeah. So the full policy will become a molecule later. Yeah. So we are still in the atoms. Okay. So for example, the 4-lane urban street is being converted into a lane street with center, for the bike lane. So in that case, you need to reduce the capacity, yeah? And then you add, yeah, for the bike. Yeah. Later you can combine this together into molecule. Clear? Yeah. So next atom is changing the properties of the link. Yeah. So this is changing in the structure of the link itself in the network. Yeah. So add links, remove link. Yeah. Add links, remove link. Yeah. So delta is changed. Yeah. A is the adjacency matrix. Yeah. This is, remember in the diagram of my logo, that if you change the adjacency matrix, everything else changes. Yeah. Okay. So you practically adding or removing the infrastructure. This is expensive. Okay, this policy is expensive. So if you want, try to improve efficiency first, than doing this. Yeah? But this is an atom of adding links or removing links, yeah? And then you put the location. Yeah? So where it is. So add links can be used to model a new road, say new railway, new pedestrian path, right? And the remove links means you decommissioning infrastructure, yeah, closing the road for good. Yeah, maybe for from the car you put it into pedestrian only or into public park and so on. Clear? So this is an example. Okay, the drawing is not so clear. So here is the scenario that we use both. Yeah, so we are building a new access road for the development. Okay, and then so we need to add the links at the same times. As part of the same project, you are removing the old road. So you remove the redundant road here. Yeah. So and then convert this into parkland, for example. Yeah. So in this case, you can see we combine the 2 atoms, yeah, into molecule actually. Yeah. Union, this represent N. Yeah. Is it clear? At the same time, yeah. So union mean you do these two atoms at the same time, in the same time frame. Okay. The union operator, no worries, we will discuss later in module 3. Yeah. Yeah. Next is to reverse the direction. Yeah. So this is also very important network atoms. Yeah. Ref dir mean reverse the direction. So this is the symbol. Yeah. You change the direction. So reverse the legal direction of the travel of one-way link. Yeah. So what is the purpose of changing the direction? Yeah. You want to reduce the traffic conflict. Yeah. Say, for example, you want to make it from two ways into one way. That means you actually add the capacity also, isn't it? So, in one particular intersection like this, yeah, you have 32 conflicts. Yeah. How many? Yeah, 32 conflicts. Yeah. So these are the diverging conflicts. So you divert from one in split, yeah, and then merging, yeah, put them together, and then there's a conflict, crossing conflicts. Yeah, these are dangerous. Crossing conflict are dangerous. So if you can reduce the number of conflict in the intersection, okay, then the traffic signal timing will actually improve, yeah, because now more vehicles can pass within the same time. And okay, so these are one of the goal in reducing the number of conflict in the intersection by changing the direction. Yeah. Yeah. So let's practice then. Right? Let's do a quick knowledge check. Okay. Take a look at this scenario. Okay, test for your recitation. So we are going to reverse one-way street, yeah, but only during a specific time. So my question to you, which atom will do that? Yeah. How are you going to put the time constraint? Okay, so who can answer that can raise hand and tell. What is the atom of this? This is the test. Yeah. So next week when you have the exam with exam similar, yeah, similar question like this, but multiple choice. Yes. Do we have the answer here? Okay. Okay. Hmm. No, not ref tier, okay? Not ref tier. Okay, you think this is a ref tier, but this is actually what is the atom? Check the periodic table a while ago. check the periodic table. Anyone can answer this? Yeah, you can type, no problem, in the chat if you want. Show to everyone, no problem. No need just direct message to me. You see here, there is a time, right? So you need to put the time also. You have the location, okay. What is the atom? Is this permanent or temporary? Wow, super. Lian, very good. Yes. Yes, temporary reptilia. That's correct. Okay. So excellent. Okay, so this is the answer. Yeah. So you need to put the temporary because there is a time, you see. Okay, nice. Yeah. And then the location. Yeah. This is for all for all vehicles, that means no more. Okay. So look at the key elements here. Yeah? Time meaning not permanent. Reptil is the actual action. Yeah. And then this is the time, isn't it? That you can put the specific time. Super. Yeah. So you make it good now. Okay. So don't forget to claim your recitation, Dian. Huh? Later. Okay. So next is the supply side, yeah, of the infrastructure. With a while ago was the supply side, yeah, meaning the network. Now the demand side. Yeah. Yeah. We shift from the supply side to the demand side. Yeah. So we have what is called demand atom, yeah, at demand or a reduced demand. Yeah. So this model will increase the number of trips. Yeah. So we are not just building the road. Yeah. We also wanting people to travel more. Yeah. Okay. And this is essential for modeling, yeah, on the impact of the land use change and so on. Yeah. So say you have new residential development, new office park, new major attraction. So you can do a policy impact. Yeah. What is TIA, traffic impact assessment. Yeah. Using this. Yeah. So so if you have an increased demand, travel demand in certain area, okay, so this is also an atom, yeah, that trip generation on the infrastructure itself. So you get up demand in certain zone, okay. So this is also a policy. Yeah. Similarly, of course, you can also have reduced demand. Yeah. Okay. Next practice then. So in this example, a new university campus will be a major trip generator, isn't it? So we can model this new travel demand. Okay. What is the atom? Permanent or temporary? Can you be specific? Yeah. So now if the university have a good transit plan, it may model a large increase in the demand for the transit mode, isn't it? Maybe a smaller one for the cars. So this will allow us to see, okay, the existing transit infrastructure can handle this or not. Yeah. So the simple question is which atom you will use. Yeah? How are you going to write it? Anyone? Okay. Yeah. Yes. Okay. Justin, very good. Yeah. So you just add demand in the campus zone for the transit. Yeah. So this model will increase the travel demand. Yeah. For the transit mode to and from the new campus. Okay. So if you want to add another atom just only for the car, so you can also add like this. Yeah. This is the add demand campus zone in the car. Okay. Yes, Justin, you want to ask?
Uh, Sir, I have a question. So for each different mode of transit, you have to create a new atom for it.
No, no. If you don't put, if you have different transit, yes. But
Okay.
if you don't put any mode, that means for all.
Okay, sir. Thank you, sir.
Because mode is optional, right? So if you don't put, that means for all. If you want to be specific, then you need to put. But if you have different type of transit, okay, you have jeepney, you have LRT, you have MRT, then you need to put one by one.
You can add another comma after transit then.
Not comma, union later.
Okay. Okay.
Yeah, the later we discuss about the molecule, then you can combine. Okay.
Okay, sir.
Our goal is actually to create very complex policy. Okay. But whether your policy looks like complex, you can break it down eventually into atoms. Why you put it into atom? Because the atom is the one that you can input in the computer, isn't it? For the simulation. Right. That's why we put this. Yeah. So we said we analyze, we can also synthesize later. Yeah. Slowly. I'm still in the atom now. Yeah. Okay, so you can also reduce the demand. Yeah. Yeah. So this is the opposite of adding demand, right? This is also powerful atom. Yeah. You can use this for design to reduce the number of trips. Yeah. Using travel demand management or TDM. Okay. For example, you want to have congestion pricing. This is actually the atom for congestion pricing, isn't it? Reduce demand in CBD zone for car only. Right. So, for example, you want to promote teleworking, or you want to have successful campaign encouraging the shift to other mode. Yeah. So you can have this kind of reduced demand atom. Okay. So remember, depends on the goal. Yeah. The goal is to eliminate or to reduce the number of trips. Yeah. For certain specific mode. Yeah. It's not the people that we reduce. Yeah. Not the number of people trip, but we reduce the mode. Okay. Of demand here. So we can also reduce for a specific target or specific mode or specific time. Yeah. So this is the demand atom of reduced demand. Yeah. So example. Yeah. This is a very classical example. Yeah. Congestion pricing. Yeah. So the entire goal is to reduce the demand for car. Yeah, in the specific area. Okay, at specific time. Okay, so you can model this perfectly using temporary reduced demand. Yeah. Okay, so the temporary reduced demand for downtown. Yeah, for the car, apply only for the peak hour. So this will allow us to test different pricing level, okay, whether the coefficient of the atoms actually improve or not. So you can have many different policies. The same atom here, but later you can change the coefficient, right? How much you want to reduce. Yeah. So next important atom is control. Basically not necessary traffic signal as long as you change the stochastic matrix. This is also the same delta S. For example, you are using Google Map or you introduce a new ITS, Intelligent Transport System, to guide the people, the trips. Practically, it will change the behavior, right? The travel behavior. And that means the probability in each intersection to move left, turn left, turn right, or to go straight is changing. So, or maybe you want to do traffic signal optimization. So this is also delta S. Notice here, delta S do not have plus and minus. Why? Because one part is plus, the other one must be minus anyway. Okay, because the total sum of probability must be 1, right? So this is crucial, cost-effective way to improve the traffic flow. So if you can have coordinated traffic signal along a major avenue, to create a green wave, and then when it near the next intersection, then green again. So then it will fasten your movement, isn't it? So you can create adaptive traffic signal to respond to the real-time traffic. Again, this is an example of optimizing the signal. Is it clear? This is the atom that you can use. I think one of your group project is doing this. Okay. Next, these two atoms, increase speed and decrease speed is also very direct, I think. They used to model the change in the legal or posted speed limit, in certain road segment, isn't it? So you raise the speed limit on the highway to increase the speed, So, and you implement the lower speed limit in residential area or the school zone for safety. So you can decrease the speed limit. So of course, changing this will directly affect the travel time computation and the delay, right? So these are atoms. Don't go another way around. So don't put increase the speed in the school zone and reduce speed in the highway. So you remember the road hierarchy. Okay, the goal is in the residential area in the school zone is accessibility, not speed. While in the main road must be the goal is increase of the travel time, reduce of the travel time. That means increase of the speed. Okay. So this is an example, how we will combine. So union here is mean the and. So this is the example that you will combine the control atoms. So for safe route to school. So this is now you have the package of intervention. So say the city program to improve the safety around the school. So you want to lower the speed limit and then you optimize the signal for pedestrian crossing. So these are the policy molecule. Remember the union here, U, that union that rests on N. Okay? Is it clear or not? So we use the temporary decreased speed atoms to model lower speed limit during the school hour, right? And then at the same time, remember N means at the same time, we use the temporary optimization of the signal atom to give the pedestrian more priority at the crosswalk. So this is perfect example how you can have combine multiple atoms into coherence policy molecule, isn't it? Yeah. So let's practice, yeah. I give you the answer already. I'm supposed to hide that. So say you want to prepare a major marathons. So then of course you will lower the speed limit in that certain coastal road, and then you retune the traffic signal, right? So when you retuning the traffic signal, that means up signal in the same place, and then you decrease the speed. Because this change is not permanent, it's only for the event, so you put 10, right? Because you put both of them must be at the same time frame, then you put union. Yeah. So this means coordinated single plan. Yeah, you connect them with union operator. Clear, yeah? So using this, you can start to see, we are going into precision, rigorous language. Okay. Yeah. Seems like, why should I do that? Again, in the motivation in the beginning. Yeah. So by doing so, you can be checked, auditable, objective. Yeah. You can simulate. Yeah. And you can also share. Yeah, this is the goal. Yeah. Now let's see the distinction between temporary and permanent. Yeah. So in the permanent, we use the upper level delta, uppercase delta. This, yeah. And temporary, we use lowercase delta. Yeah, this is the crucial distinction. Not all policies are forever, isn't it? Yeah. Our language will handle this, two different symbol, different naming, convention. Yeah. So one is permanent change, the other one is temporary change. Permanent change means lasting, structural change. So you can have this kind of symbol. And temporary change is just time limit. Can be permanent all the time, but within certain time limit. Usually, if you use temporary, you will put the time during Sunday or a weekend or peak hour. So that means if you put temporary, it requires a time annotation when it will be applied. Clear? The time annotation is optional, but in the temporary, you're supposed to have that. Okay. So say lane closure during the weekend festival. You can use that. Certain demonstration in a certain part of EDSA, then you can use that. And then you can simulate and then how the traffic will change. Okay. And then you can suggest which route you're supposed to inform to the public. Yeah. So this is very interesting language. Yeah. So let's now focus on the specific time. Yeah. So how do we specify the time for the temporary atom, right? Okay. So we use at time like that. Yeah. This is very flexible. Yeah. So you can define it as a precise time window. Yeah. From what time to what time, or you can, yeah, you use a 24-hour format, yeah, so that easier. And then you can use name event, yeah, for example, weekend, yeah, or marathon day, yeah, or during the festival, yeah, yeah, or during emergency. Yeah. So this model, the need, yeah, to have definition. What is that event means? Yeah. So using this, you can have a very intuitive policy writing. Okay. Okay. So you can either use time interval or using name event. Okay. Uh, Underscore. Yeah, not using space. Yeah, so you use underscore. Otherwise, the validator will not uh, put it right. Okay. So let's practice this. How are you going to model this as a policy atom? Say, this is a classic urban planning policy. Weekend pedestrianization. Yeah. You are trying to remove the access. How are you going to put this? Say you are targeting only for, oh, this is for all vehicles, no? How are you going to put the policy? Atomic policy atom. Anyone? Yes, Ken.
Small delta A minus at weekend, sorry.
Okay, what is the action?
Remove link,
Hmm?
temporary remove link.
Oh, okay. Temporary remove link, yeah. So temporary remove link, yeah, in the shopping street, okay. So this is all vehicles, so that means no mode. And then at weekend, yeah. Okay. Oh, then I have it. Okay. So if you put it only for cars, then of course you can add car. Yeah. If you don't, if for all vehicles, you don't need to put the cars. Yeah. Okay. Super. Yeah. Thank you, Ken. Okay. Okay. Next practice. This is to support Downtown Food Festival on Saturday. Yeah, from 10 a.m. to 11 p.m. Yeah, you want to close, yeah, the main street to cars, and then you will add temporary demand for pedestrian. So how are you going to put this into policy molecule? Yeah, this is the illustration, right? You can have a food festival like this. Yeah. Remember, this one had two parts, okay? So we need to close the street to cars, and at the same time, that means union. Okay, so you model the extra pedestrian, okay, to the festival. Anyone? Yes. Temporary remove link, yes. 10 to 23, correct. And then optimal, yes. Super. Justin, yeah, super. Yeah. So, yes. So, temporarily remove. Yes. Yeah. So this solution have to that molecule have two atoms. Yeah. The first one is temporary remove links, yeah, for the car. Okay, and then have specific time. Okay, and then the second one, we use union operator because at the same time, okay, we also add the demand. Okay, for pedestrian. Okay. So also at the same time. Yeah. So this show that everything that we have learned. Okay. So you have the atoms, you have the mode, you have the temporal chains, you have the times. Okay. So and then you put them together, yeah, to build the complete policy. Yeah. So great job. Yeah. So let's go to the next module. Yeah. We will formally dive into the operator. Yeah. That connect these atoms. Yeah? So let's go to the operator. Okay, we have three operator. Okay. Now we want to create a policy molecule. Yeah. So if atom is a single tactic, right? So like a single gear. Okay. So the molecule is a complete strategy. Yeah. So you have a full assembled gearbox. Yeah. So you can define the relationship between individual actions to create a cohesive plan. Okay? A simple molecule contains just one atom. Okay? So atom can be a molecule can be just one atom, possible, right? But actually, when you have several atoms or even molecule combined with atoms and molecule combined with molecules, and then combining this become very sophisticated, yeah, and then closer to the real world intervention. Okay, so you can create a multi-stage plan actually, using logical operator of union, arrow, and tilde, yeah, not. Just three logical operator is needed. Yeah. So these are the three logical operator. So when you want to connect our atoms, yeah, we need a grammar, isn't it? In our language, this grammar provided by just three simple, powerful, yeah, logical operator. Okay. So one is the union, represent and. Yeah, meaning combined with. Yeah. The second is sequence. Yeah. Arrow operator means then, yeah, followed by. Yeah. And the third one is negation, not. Prevent this. Yeah. So this is represent the exemption, constraint. Yeah. So we will explore more detail, yeah, each of these. Yeah. But just remember this, yeah. We have only three operator, yeah, and then not. Okay. So these are the foundation, yeah, to build any complex policy. Okay. There is another operator actually, but this is not logical operator. This is just equivalent symbol just to assign. Okay. So this is operator to define the name. Yeah? So this is no executable, no action. Okay. So the purpose of having definition operator is to make it simple, human readable name, yeah? So that you can reuse, right? So that you can have modularity, okay? So when you have the name, then you can have same as if this is a module, okay? And then you can reuse for the next combine with the other molecule, okay? So it's like a naming of a chapter in the book, yeah, or a function in the program, computer program. So it will make our work cleaner, easier to understand, yeah, and allow us to reuse a common policy pattern, yeah, without having to write them out every single time. Yeah. And this is actually the key to manage the complexity, yeah. Naming. Simple. Yeah. So this is an example of defining the molecule. Yeah. So say you want to relocate the road space in the main street from car to bus. Okay. So then you can give a name, bus priority. Yeah. This is the name of the molecule is bus priority. So you define with this equivalent operator. Okay, so what is bus priority? Yeah? It is a simultaneous combination. Why it is simultaneous? You have union here, that means simultaneous. Okay? Of two atomic action, yeah? Reduce the capacity for cars, yeah, on the main street, and then add the capacity for bus in the main street. Yeah? So now, then from now on, whenever we use the term bus priority in a policy, then the system will know that you are referring this exact combination, yeah, of action. Yeah. Is it clear? So why naming is very powerful? Yeah. Because of the power of modularity. Yeah. Why you need to trouble the giving name? Yeah. So because it allows us to manage the complexity. Yeah. This is the principle of modularity. Yeah. Look at this example. Okay. So we now can create a new larger policy named main street upgrade. You see here, there is a bus priority. That means previously defined, yeah, earlier, this one, the bus priority. So you don't need to redefine, yeah, because once you define, you can reuse. And you see this? Yeah. So we define it, okay? The main street upgrade represent the bus priority and optimizing the signal, yeah, in the main street. Yeah. Without this, what you will do, you will combine all, right? The three of them. Yeah. You will combine the three of them together. Yeah. It is also the same, yeah, the same policy, but now you can reduce. Yeah. Simplify. When you have the two version, yeah, they are exactly the same, yeah. But the bottom version here, well, this is technically correct, yeah. Then when you have a lot, become clutter, yeah, harder to grasp at glance, isn't it? So when you have a lot of policies and you combine, say, a dozen of atoms, yeah, this practice of naming and layering become absolutely essential, yeah, to create a transparent and auditable plan, right? Okay, now let's dive into our first and most common operator, which is union. Yeah. This is the symbol union. Okay. So this operator simply means and. Okay. So you use it when you have multiple action, yeah, that are part of one single policy package or molecule. Yeah. So and then this also means they are applied at the same time. Yeah. Order does not matter. Okay. Say if you want to reduce the capacity for car and then adding capacity for bike at the same project, then you can bundle this into one molecule using union operator. Now, the use case is, remember this, yeah, implement together simultaneously. Yeah, that is the most important keyword there. Yeah? In parallel, and order doesn't matter. So that is where you will use union. Okay, so think of this like a checklist of the project. Yeah? If your items are part of the same plan, you use union. Clear? Yeah. So the syntax is very simple. You have atom A or a molecule A, yeah, union with atom B. Okay. And in the syntax, yeah, spacing is required. Yeah. Remember, when you put it into validator, if you don't put space, it will not say correct. Okay. So, and then you cannot put union in the beginning. Because union is a binary operator, so you need to have first atom and second atom. Okay, these are the syntax. So very straightforward, but also very strict. Yeah. So you simply place the union between the two atoms. Yeah. So the most important rule is to remember you need to have space in both sides of the operator. Yeah. Okay, so using this space, computer will correctly parse the policy string. Yeah. Without that, computer does not know, right? So think of this atom as word, and the operator as the conjunction. Yeah, they need to have space to be read correctly. Yeah, this is an example now. Yeah, you have seen this actually before. Yeah, now let's give a formal operator. Okay, so a road diet that reduce the car lane and then add the bike lane. Yeah, so you can have this is the policy molecule. Yeah, so how many lane that you reduce for the car? Two. Yeah, so the two here represent the two car lanes that you reduce. Yeah, in addition, okay, you add bike lane. Yeah. Yeah, so this is a package deal. So you add this. Ah, another example here. Yeah, it become example because I did not hide it. Yeah. So say you want to close a street in central business district for the car on the weekend and then encourage the pedestrian activities. Yeah. So then you use union also. So weekend plaza. Yeah, say this is the name of the molecule. Yeah, it will have a pedestrian zone on the weekend. So you need to first close the street to the car. Okay. In this case, you need to have temporary remove links, right? And then you want to model the effect of the space to become more attraction. That means more pedestrian. So in this case, add demand, yeah, of the pedestrian. So, and then both are in the weekend, yeah, because this is temporary adding demand. And then you put union to unite them. Okay? Clear, yeah? So, this is when you will not use union. Yeah. So very important, okay, to know when you should not use union. Yeah. Union is only used for concurrent action. Okay. Think about setting up a detour for the road construction. So you absolutely need to build and open the detour route before you close the main road, isn't it? So in that case, you should not use union. Yeah. Why? Because union means exactly at the same moment. But in reality, detour must be ready before the closure. Yeah. So yeah, if you have sequential plan with order matter, don't use union. You use arrow. Yeah, you use then operator. Clear? Careful, yeah. When you use union, yeah, it should be at the same time. Okay, so let's go to the next operator, the then operator or the sequence operator, yeah, with arrow. Yeah. The sequence operator define the strict order of series of action. Remember, we have parallel action, we have serial action. Okay, so parallel action you use union, parallel action you use union, serial action you use arrow operator, yeah, then or followed by. Okay, so the meaning is simple and intuitive. Then, so you use this operator when you have the order in your policy. Yeah, your order is critical, so then you have to use this. Yeah? So this represents the cause and effect before. Yeah? So action A must be completed before action B begin. Then you use arrow operator. Yeah. Okay. Action A happen first. Only when it's complete, then action B begin. Okay. So the syntax is the same, yeah. Just add operator arrow between the two atoms or the two molecule. Yeah. Again, if you want to use this, spacing is required, yeah, between the two atoms or the two molecule, and then you cannot use arrow in the beginning, yeah, or in the end. You must, because this arrow is a binary operator. So you need to put between two atoms or two molecules. Clear? Yeah. So again, yeah, this is essential for parser to correctly read your policy, understand the intended order of operation. That's why you need to have very strict rule, yeah, for the syntax. Yeah. So here is very clear and intuitive example. Say you cannot optimize the traffic signal and that does not exist yet, right? So then the logical demand is you need to have the policy of add node atoms, yeah, say in that intersection, followed by the sequence operator of optimizing the signal. Yeah. So first you build that, if the node does not exist, yeah. So you need to add that roundabout, okay, and then you create optimizing the traffic signal. Yeah. So say if you want to construct a new roundabout. Is it clear? Yeah. This example of sequence. Yeah. So this is another example. So you have, in this case, time critical, yeah, real world example, incidence response plan. Okay, so in this case, order matter for safety and efficiency. So you must create a detour or emergency access before you shut down the lane, yeah, where the incident occurred. So in this case, you have sequence operator, arrow, yeah, to enforce this logic perfectly. Yeah. So you have the temporary adding lane for the emergency access should happen first, then temporarily reduce the capacity in that lane number 3. Okay. By having precise language, yeah, so I think you can communicate better also to the implementation, isn't it? Right? Any question so far? Yeah. So now you need to distinguish, yeah, between union, U, yeah, and the sequence operator, the arrow. Yeah. So choosing the right operator is critical for your policy logic, right? So look at this. Union mean and, yeah. Arrow mean then. Yeah. That means structurally you have parallel processing, yeah. While in the sequence you have serial processing. Yeah. Remember, in union the order does not matter, while in the sequence order critical. Yeah. So you use this union if you want to combine into a single policy package. Yeah. While you use the sequence operator if you have the phasing plan, yeah, multi-stage plan. Okay. Yeah, these are the example here. Yeah. What is this? Can you read? This one is reduce capacity for the car, yeah, and then add capacity for the bus. Yeah. So in here, you add the link for the tour first before you remove the bridge, yeah, link on the bridge. Yeah. So these are the phasing plan. I hope this is clear enough. Now, there is the third operator, logical operator, which is not, yeah, negation. Negation express constraint or exemption. Yeah, this is a little bit different. The union and then operator were binary. Here is unary. Okay, the meaning is preserve to not take this action. Yeah, to not take this action. So this is it does not combine two atoms. Yeah, it's just applied to single atom or single molecule. Okay, so the meaning is not. You use it when you want to build constraint into your policy, saying apply this action everywhere except there. Yeah. Make sure that this action is prevented. Yeah. So you explicitly state that this action must not occur on the specific target. So if you want to create exception, use not. Okay? I give you an example now. First, syntax first, yeah. So the syntax, you don't need to have space, but you can have space also, yeah. So both are okay. Remember, this is unary operator, so it applies to either atom or molecule, yeah. Okay. So negation is a prefix, so you place it before the atom. Yeah? So now, all right. So now you have the theory of the three logical operator. Yeah? So now is the time to practice. Okay. Now to practice. Yeah. So I'm going to present you a few scenario, okay? And then each one, your goal is to write the correct policy molecule, okay? So the key is to analyze the language of the scenario, and then you figure out what is the logical relationship between this action. Is it a package? Is it a sequence? Or is it an exception? Okay. Are you ready? Okay. So here is the perfect example use case for negation. Yeah. Imagine you want to run a signal optimization algorithm on every traffic light in the city or in the district. Yeah? But you have a very critical emergency route at the hospital, one hospital, where the existing signal timing is sacred. You must not alter this. Yeah. So then you can write this, okay, optimizing all the signal for all intersection, and then union with except. Yeah, this not mean except. Yeah, exception. Okay, for you forbid the optimization in the hospital now. Is it clear or not? So yeah, by putting this way, you have now exemption. Is it interesting now? Now you can create logical operator in your policy. Wow, super, right? Okay. So a city want to permanently calm the traffic in the residential district. Now the policy has two goals: slow down the current traffic and ensure the traffic never widen in the future. Okay, can you write the molecule? Can you write the molecule? Okay, so it's clear. You want to slow down the cars today, and then you forbid the future capacity expansion. Yeah, so there's a hint here. Yeah, so you can slow down mean decrease speed, right? Okay, capacity expansion mean add cap. Okay, so you can use this operator and then you combine with the definition operator. Okay, try. I hope this is easy practice. Yeah, the answer in the slide, but try to do it on your own. Yeah. Yeah. Think about how you express both part, okay, using atom and operator, okay, so that you can say Elm Street permanently quiet. Yes. Okay, so decrease speed, yes. And union, very good, yeah. So you can have, say, for example, certain street. Yeah? So quiet street policy is equal to decrease speed, yeah, of your street, okay, from the car, okay, and then this is the exception, yeah. So you forbid permanently, yeah, because this one have no time, right? So this is permanently you forbid them for widening, yeah, road widening. Yeah, interesting, yeah. Yeah. Thank you, Lian. Yeah. I hope the others can also make it clear. Is it clear or not? Yeah. So by looking at very down atom and then you can combine the molecule, yeah, look like a games, eh? But at the same time, I give you the validator, I give you the atom builder there, yeah. So then actually now you can enhance your own creativity, you know, you can create your own policy, isn't it? Interesting, yeah. Yeah. So, do you know RAM metering? Yeah, this is in Wikipedia. Yeah, so RAM metering, yeah, is a traffic signal in the freeway. Yeah, so it actually is a very smart way to manage the traffic congestion in the freeway. Yeah, instead of letting all the cars flood at once. Yeah, so you need to use a signal, yeah, to space them out. So this will prevent the bottlenecks, yeah, and keep the traffic flow, yeah. And then high occupancy vehicles, for example, bus and carpool, usually have bypass so that they are not delayed. But the car need to use the RAM metering. Okay, so the point is the RAM meter basically a traffic signal that placed on the freeway entrance ramp. Okay, they will temporarily stop and slow down the vehicles before they merge into the main highway. Yeah. So usually during the peak hours, yeah, the RAM meter will turn red to hold the vehicle backs. Remember, road hierarchy. Freeway is the highest, right? So that means they need to flow full, yeah, in full speed. Okay? The one that want to enter will be blocked. Yeah. So that means during the peak hour, it will turn green briefly only, allowing a few vehicles to enter the freeway. Okay. And then turn red again. It will create the spacing between the vehicle to merge smoothly, yeah, into the main freeway. Is it clear? Yeah. Yes, it will create congestion back in the normal road, not in the freeway. This means prioritizing the freeway. Is it clear? But at the same time, yeah, it often used to encourage people to use HOV, yeah, high occupancy vehicle. Yeah. If you use car more than 2%, you can pass faster. So that is a bypass lane. Clear, yeah? So now the next practice, yeah, is about this RAM metering. Okay. So yeah, so RAM meters are used to regulate the flow of the traffic into the highway, but the bus and high occupancy vehicle (HOV) are exempt and can bypass the queue. Oh, this is very classic but very powerful negation, isn't it? Exemption means negation. So the general policy is temporarily reduce the capacity on the ramp. Yeah, exactly that's what meter does, isn't it? Temporarily reduce the capacity on the ramp. But we want to create an exception. Yeah, we do this by adding negated atom. So, okay, try. What is the molecule policy of this? Yeah. So you want to create a bypass. Yeah. So you want to say, apply this capacity reduction for all RAMs, but do not apply this same capacity reduction to HOV with 2 or more person. So, how are you going to write that? Mhm. Temporary or RAMs? Yes. Hmm? Oh, okay. Yes. So, right. So you can have, say, we call this meter policy. Yeah. So this is a policy that temporarily reduce the capacity for all RAMs. Yeah. Union, yeah, not them, right? So with the exception, yeah. Exception, the same, yeah, the same action, okay, but now you have not here represent exception for HOV, yeah, high occupancy vehicle of 2 and more occupants. Okay. Nice, yeah. So yes, Justin, you want to say something?
Sir, I'd like to ask about the equivalent policy, the meter underscore policy.
Yes.
Does it have a specific name to it, or
No,
it
you
depends on what?
the name is you define. Yeah. So meter policy means you define the name.
Okay.
Okay, so this 3 bar or equal, yeah, this is represent equivalent. Okay, this is to define the name.
But we can generate our own name
Yes,
for that.
exactly. You need to generate your own. Okay, you can even name it Hasegawa policy, but no problem. Yeah. Okay.
Okay,
So
thank you.
yes, Lian, you want to say something?
Sir, question also. For the high occupancy vehicles, do we have to specify the number of occupants like we did in that example, or
Yeah, in
it's
this
also
case, you can define. Yeah. If you want to define exact number of occupants, for example, 2 and more, so we can put SOV2 and so on. Okay. But if you don't put, that means you define it somewhere else, not in the molecule. Yeah.
okay. Thank you.
So the chemistry of transport policy help you to define it more rigorous. Okay. But later, when we discuss later with the model, yeah, you actually need other models, yeah, to combine this together, yeah, not just the chemistry, yeah, to implement this later on, yeah. So in that case, if you have the SOV 2 or 3, yeah, you are the one who define. Okay. So this is the explanation of earlier, yeah. So in general, you have temporary reduction of capacity for all RAM. Okay. And then you also have exception, which is again the same atom here, temporary reduction of capacity for all RAM. And then, but only for SOV, and then you put not. That means do not reduce. Yeah, do not reduce capacity for SOV. Yeah. And then when you put combine with union, that means apply put at once in parallel. Yeah. So that means you have the general rule and then you have the target exemption here. Yeah? That means the meaning of this policy means regular car weight, but the high occupancy vehicles, including the bus and so on, will have a bypass. Imagine you have a precise language, to build your own logic of policy. Nice, yeah. Okay. With this, you can communicate better, isn't it? Huh? So I hope this is useful, yeah. So again, yeah. So the part here, is the regular car. Okay. You have the RAM meter with the red light. Okay. But if this is VOV, HOV vehicles, so you always green. Okay. So except for carpool, for buses, and so on, so they get timers. So by creating this kind of exemption, okay, people will be encouraged to use bus, to use carpool, isn't it? Yeah. So by having this kind of policy, you start to think, yeah, policy is not always wide road widening, right? So you can make exemption like this, just traffic signal only. Yeah? Make them suffer a little bit, and then you give exemption like that. Yeah. Yeah, okay. Now you have more complex. Okay. Now you have a more complex molecule. Yeah. This is a practice so that you can get the understanding how to build, isn't it? So this is not the scenario. Now you have three sub-policy, not two. Yeah? Now you have three sub-policies. Yeah? So how are you going to combine them into a hierarchical molecule? Yeah? Try not to see what is the answer in the slide. Try to do it on your own first so that you can think. Okay. So the scenario is as follow. Yeah. So you have the RAM metering a while ago. You also have the HOV bypass a while ago. So you already have that too. Okay. But you need to add one more. What is that? Incident override. Yeah. So you have the signal to override, signal override during the incidents. Okay. So this will help you to think. Yeah. Yeah. How are you going to build complexity in your composition? Yeah. So remember, each sub-policy must be clear and reusable. So, yeah. So you can use definition operator, you can use union, and then you can use arrow. Yeah. For sophisticated RAM metering plan that include SOV bypass for normal operation and a signal override protocol for the incidents, contingency override. I tried to use AI to generate that. Yeah? So you see here image. Yeah? So there is a SOV bypass lane, but RAM metering is suspended during the incident. So then incident ahead. So if there is an incident, this is suspended. The RAM metering is suspended. Oh, how are you going to make that kind of policy? Create the policy molecule to do all these three. These are the three. Yes, Justin.
Just a question, sir.
Yeah.
For this instance of the problem, do we have to define a specific peak hours, or can we just say at peak hours?
You can say at peak hours.
Okay, thanks, sir.
Yes. Yeah. When you practice this, what is the policy molecule? Yeah, this is a real world challenge. Yeah. Is it difficult? Okay, so the first step is you need to get the building blocks. Yeah. See, for example, this is one of the okay. So you get the simple atoms to a policy that's truly complex. Yeah. So the answer is actually hierarchy. Okay. So you don't write one massive unreadable line of code. Right? So instead you build the policy like so engineer build the machine. Yeah? From small, you assemble the module and then now look at this RAM meter example. Okay? So we define the three core component, isn't it? So we name it metering. Yeah? So temporary reduce. Yeah, this is metering at certain time, right? So and then we have the bypass exemption. Okay, and then we have also the emergency override. So we put them, we keep name for each. Okay, so we keep name. One is name metering, the other one is bypass, and then the third one is override. Okay? We keep name three of them. Okay. After we have the three of them, then we define a new policy, say SOV run policy, for example, okay, which is actually these two must be combined with union, right? This two is actually the run meter we bypassed a while ago, the previous example we already discussed. But we also have this then override. Yeah. So this represent the to connect, yeah, the normal everyday plan with this metering with bypass. Yeah. Then we use sequence operator to connect the normal plan with our emergency override plan. Yeah. So this final molecule is actually very beautiful, capturing the full logic. Yeah. So you can run the normal plan, which is then superseded by the override when needed. Yeah. So this is the power of the language. Yeah? So you can combine these simple logical rules. Okay? Then you can build a policy for any complexity. Okay? So, and every single part, yeah, is transparent and then auditable. You can audit the policy. Yeah. This is the most important part there. Yeah. So one by one you build and then you combine. Okay. Okay. Next practice. This is the next practice. How are you going? Say there is a climate plan. Okay. You want to have three-phase plan. Is that three-phase? Climate plan. Phase one, three-phase or two-phase? Okay, anyway. So phase one is concurrent. Yeah, you have to ban the diesel car wide, citywide, and then you create the permanent exemption for existing diesel bus. So this is the phase one. So three phase, and then the third one is or phase two. After the ban is effective, then you add new electric vehicle charging station. So how are you going to model this? How many atoms? Three, right? Yeah, three. Yeah. First is banning the diesel car. Okay. And then second is you create exemption. Remember, exemption means you have not. Yeah? So the existing diesel bus. Yeah. And then what happens if you have sequential? You use arrow. Yeah. Okay, try. I hope by practicing this chemistry of transfer policy, yeah, you start to think policy logically, right? Yeah. Before you start to say, "Oh, I want to do like this, like that," but based on persuasion, yeah. Okay, but I want you to do it precisely. How are you going to implement that in the simulation? Okay, then you write it down into a atomic or molecular policy. Okay. With that, your friend can have the same meaning, non-ambiguities, yeah, the same meaning for the language, because computer have the same understanding with you. Okay. Is it clear? Yes. Yes. Union. Yes. Very good. Yeah. So yeah, this is in the yes, this is in the slide. Yeah. So correct. Yeah. Thank you, Justin. Yeah. So the answer is very simple. Yeah. You get one by one, and this is exemption. So that means you put not there. And this is you need to do this first before you go to the next one. Yeah. Okay. How about this one? Can you write this policy molecule? So you have your city, yeah, plan to upgrade the major corridor. Yeah. So now you have two action plan. One is permanently increase the speed limit, and then you retiming the all traffic signal, yeah, coordination. So what operator are you going to use? Union or sequence? Or not? Negation. How are you going to write this? Okay. So Lian answer, yeah. So you need to increase the speed first, yeah. And then at the same time, yeah, you also optimize the traffic signal, yeah. So in this case, this is concurrent action, okay. So you use union, yeah. So the keyword is actually the same construction package, yeah, a while ago, yeah. So this means this is concurrent action, yeah, in parallel. So in this case, you use union, okay. How about this one? Say you want to promote bus transit, yeah, the city is adding bus only lane, yeah, to all major avenues. However, the plan also explicitly say that the Elm Street, this is a narrow historic road, must be excluded from this change. You have exception. What you will do? You put no. Can you make it? Okay. Try not to use, try not to see the answer. Try to use your own answer first so that you can practice. Is something hard or easy? Yeah. So this exercise introduced two constraints. We have a broad citywide action, okay, and then with one specific exception. Yeah. So how are you going to model everywhere except here? Yeah, you use no, yeah. So you see here, adding exemption is okay. So bus lane is for all major avenues, right? For the bus, you add capacity for the bus, add lane for the bus, and then except for this road, yeah, except for this road, yeah. So when we say except, mean you have negation symbol here. Is it clear here? Yeah. So because of this exemption, yeah, it's a part of the overall plan. So you use union. Okay. So that means you can read this as add the bus capacity to all major road and to not add the bus capacity to Elm Street. Yeah. I hope this is clear enough. Okay. So you can create a language that you can put here. Now, this is another practice. Yeah. Emergency response. Yeah. So you have two-phase scenario. Yeah. This is emergency response. That means what is this? Temporary or permanent? Okay. So first, you immediately close the damaged bridge, and at the same time, you reverse the direction of a nearby one-way street, yeah, as an act of detour. Yeah. And then after the phase one is complete, yeah, then you add temporary ferry service across the river. Yeah. Oh, this is interesting. Okay. You have two phase. When you see the phase multi-phase, that means you need to not at the same time. Then you need to have arrow, isn't it? So can you combine this into one policy? Anyone can answer? Yes. Okay, so yes. So first you have the remove links. Yeah, this is the answer from the slide. Okay, so this is just two distinct phase. Yeah, look at the first phase. Yeah, what happening? You have the closure and street reversal at the same time. That means you need union. Okay, so this is the remove the links of the damaged bridge and reverse the direction and the tutor street. So this is a union. Now, once you have finished this, okay, and then temporarily you add a link for the ferry service. Yeah, so that means after the arrow, the sequence operation here represent the after. Okay? So you connect the phase one molecule with the phase two atom, yeah, using arrow. Yeah, so this is the multi-phase plan. Yeah, so my question now, you have and you have then, but you don't have or. Why you don't have or? Okay, so why there is no or operator? Yeah, or is not allowed in one policy molecule. Why? Oh, yeah. Because a policy must be a single executable commitment. Yeah, it's not list of options. So if you have or, you need to make it clear that you have several alternative scenarios. Alternative 1, alternative 2, alternative 3. Each alternative policy is a molecule. Okay, so if you have or, right, example here, yeah, you add the bridge A or you add tunnel. This is not a policy, this is indecision, right? So why you exclude this or? Because a simulator cannot execute or. Yeah, you need to execute one by one. Okay, the same thing. Construction crew in the road cannot build the or, isn't it? Okay, so that is why the grammar, yeah, the language of chemistry of transport policy force this. Yeah, you decide first and then you codify. Okay, that's why you don't have or as operator. So you only have union and, okay, arrow sequence or then, and then negation not. Okay, this is enough. Okay, so policy is a commitment, yeah. So if you still decide between option, that means you are not ready to write your policy. Instead, you need to model each option as separate molecule and then simulate them, okay? And then you select among all of these alternative scenario, yeah? So if you have or, that is good. That means separate, yeah? Separate scenario. After that, you can evaluate, you can simulate, and then select. Yeah, you choose one of them. Is it clear? Yeah. Policy means commitment. Remember this. Yeah. So now, how do we model alternative? Yeah. Then you follow the scientific method, right? So we treat each option, okay, as a separate testable hypothesis. Okay. So you create the policy molecule, okay, and then you put them into the simulator. Yeah. So here we have technology focus plan and infrastructure focus plan. Yeah. The wrong way will be to try to combine both with or. Yeah. And. Okay. So these two are conflicting action. Yeah? And this is not valid grammar either. So then the best way is to define tech plan means optimizing the signal along the corridor and then temporarily reduce demand in the corridor for the car, yeah, during peak hour. Yeah. The second one is you define infrastructure plan as reduce the capacity, yeah, for the corridor along the corridor for the bus and adding capacity for the bike, yeah, in the same corridor. Yeah. So now you have two plan as separate molecule and then you simulate one by one. Yeah. So the benefit of this is enormous actually. You can simulate the tech plans and then see the result and then you simulate the infrastructure plan, okay, and then see the result. Yeah. Now you have the direct evidence-based comparison, yeah, of the two distinct strategies, isn't it? So this not limitation of the language, yeah, but this represent you need to have enforce of clarity, yeah, that you need to compare. Okay, so now instead of debating the option, now you go to testing the hypothesis. Yeah, so as the summary, okay, you have the three operator set yeah, union, sequence, and negation. Yeah. And remember, yeah, no or operator by design. Why? We want to to enforce the commitment of the policy. Okay. And by mastering these three operators, yeah, you can translate any policy actually to have the clear testable form. Yeah. So now I want in brief give you the advanced concept. Yeah. Just brief so that you can see how it is. Yeah. Yeah. The fourth module. Yeah. In here, you want to separate semantic from the syntax. Yeah. So far, we just discussed the syntax, isn't it? The grammar rule of the language, you have validator. Yeah. Now we want to shift into the semantic, yeah? Meaning the logic, the meaning behind this policy. Yeah? In syntax means is grammatically correct or not? How you write it? Yeah, it's boring. Okay, computer can do it. Yeah, but the semantics means, is this policy logically makes sense or not? Yeah. So the policy can be syntactically valid, but semantically invisible. Yeah. So is this policy feasible or not? Okay. So this is the example, okay, of logical conflict. Yeah. Invisible. Yeah. A policy is considered semantically invisible, yeah, if you have logical contradiction. Okay, so what is that? If you have the same action A, yeah, and then union with not action A. Okay, so for example, again, yeah, adding link on road A and then remove the link on the same road. That is illogical. At the same time, no? So that is illogical. Okay, so the rule is simple. Yeah? Avoid simultaneous contradictory action on the same target. Okay, so but be careful. Yeah, a while ago we talked about union and arrow, right? The sequence. Yeah. If you put like this, add links on A and then union of remove link on A, this is conflict, yeah, invisible. But if you put this, if you change the union into arrow, this is visible. This become identity. Why? Because you first build the link A, yeah, and then you demolish it later. Yeah. So meaning identity means you come back to the original state anyway. Yeah. So be careful when you use union. Don't put union in the same action in the same place with not. Okay. So these are example of semantically invalid policy. Yeah. So you have add capacity on certain links, union, reduce capacity and the same link. So this is not valid. Yeah. The same thing, you add demand for the car and union not add demand for the car. Again, this is invalid. Yeah. But if you put arrow, this is valid. Yeah. Or if you put different mode, this is valid. Okay. Okay. Now, how do we model if then? Yeah. If then else. Yeah. The language does not have that, yeah, at this point. Okay. So in that case, you need to handle this in the external system. Yeah. So the traffic management center that monitor the congestion will know this and then will automatically issue, yeah, the policy if certain threshold is met. Okay, so this is an example. Okay, say you have the congestion-based RAM metering. Yeah, if the congestion of the toll road exceeds, say, 90% during the morning peak, then you activate the RAM metering. Okay, so the TMC or the Traffic Management Center, okay, will check this, monitoring this, and then the policy, yeah, the one that put in the RAM metering policy, yeah, this will be applied. Yeah. Now the if-then logic is not in the policy. Yeah. If-then logic is in the implementation. Can you see that? So in the application layer, so not in the policy. Yeah. So by doing this, yeah, you have the separation of concern. Yeah, this is the design principle. Yeah? So you keep the conditional logic external of the policy language. Okay, using this you can have a better simplified, yeah, policy. Yeah, and then it's also very flexible. Yeah, you can have a triggering system. You don't need to change the policy. Yeah. For example, yeah, it will be executed at certain time, yeah, say 1732, for example. So this is simple that you can lock into your system, yeah, monitoring system, yeah. So by doing so, then you can see what actually happening. Yeah, you can audit the system. You can audit your policy. So the next logical question is, what if I want to apply this action to many, yeah, different intersection for all? Yeah. Do I have to type them all out? No. Yeah. So you can also use for all command in the yeah. There is no for all in the language itself. Yeah. But because we want to hide the complexity, yeah. So instead you have two-step process. Yeah. First, you define the list of all our target. Okay. So, and then into a list, yeah, name, and then you put a simple script. So you define the list. What is your target location? Yeah. By define. Okay. 3 bar is an equivalent. After that, you generate the molecule. Yeah. So this is the example. Say you define CBD nodes. Yeah? So these are the node number that you define. Okay. After you define the node, yeah, then you create the molecule. And then you give name to this. Is it clear or not? Yeah. Yeah. So let's recap. Yeah. First, remember the difference between syntax and semantics. Okay. So our job is to make sure the policy is not just grammatically correct, but also logically sound. Okay. Second, remember that the concept of if, then, for all, yeah, is just handled by the external system to trigger this policy. Okay. So it's not about the policy itself. Okay. Next is the scoping. Yeah? What will happen if I have economic policy? What will happen if I have land use policy? Yeah, zoning. What will happen if I have behavioral policy? Can I still use this? Yes. Yeah. The language does not have all of this, right? But we can still handle. How? Yeah. Because we can have what is called two layers architecture. Yeah. So in the first layer, yeah, you have the core atomic language policy. Yeah, that is the one that we discussed today. Yeah, this is very simple, stable, and precise. Yeah, and then the second layer is the external model. Yeah, to translate this. Yeah, say for example, you need economic model, you need land use model, you need behavior model, and so on. Okay. Yeah. Then when you have this translation model, external translation model, you combine these two, okay, then you will have the entire policy that you have. Is it clear or not? I give you an example. Yeah. So the first is, of course, your core atomic language. Yeah? So you have the vocabs, yeah, the chemistry of atomic policy here. Okay, that means you need to change the network graph, the demands, okay, or adding capacity, remove link, and so on, yeah? Or optimizing the traffic signal. So this is the first layer. Okay, and then in the second layer, you have the model, another model, okay, to connect with that first layer. Yeah? For example, you have ideal traffic assignment. Yeah, you have the four-step model. Yeah, maybe after a midterm we will discuss this. Yeah, or you have price elasticity model, or maybe you have certain survey model, yeah? State preference model, and so on. So, or you have sociology model, economic model, language model, whatever model you have, yeah, in the in your own domain, you can combine this, yeah, in order to get what you want in the core policy. Is this clear? Yeah. Say, for example, you may have economic model to understand the price elasticity. Yeah. So this is the model to answer the question, if we implement this congestion charge, how much will the travel demands of the car decrease, right? So you need another model for that, okay? So the output is very complex computation, yeah? It's not long report, but then you have very simple atom, just temporary reduced demand for the policy. So the policy itself is simple, temporary reduced demand, okay, with certain coefficient, okay? But in the layer 2, yeah, it's very complex. So you can have many, how much, why is this, okay? In the layer 1, the core is just simple what. Yeah? By separating this, yeah, now you can see we think about tactical level. What kind of policy you want to do? How to do it later during modeling. Is it clear or not? Yeah. So this is an example. Yeah. So if you want to have a congestion charge, for example, then you need another model to calculate the expected demand reduction. Yeah, based on say price elasticity. Yeah. So in the first phase, yeah, atomic language is just simple like this. Okay. Another example here. Say you have a land use policy. Yeah. So you want to have a zone of urban area, okay, for transit-oriented development. Yeah. So that in the atomic policy, you will simply say adding demand of the suburban zone for the transit. Okay. How are you going to get this? You have another model, yeah, which is, for example, four-step model, yeah, to forecast. Okay. So yeah, the same thing with the behavioral model, yeah. So you can have other model to add, yeah. Yeah, with this you can have exhaustive system, meaning any policy you can model using this technique. Yeah? And second is also flexible for any future proof policy. Technology always change, isn't it? Isn't it? So what we have today does not mean that in the future we'll have, but this kind of rigorous language can be used even in the future. Okay. Now, EPNF, yeah, is the formal language of that chemistry of transport policy. Yeah, this is based on ISO. Okay, so EPNF is basically called extended Bacchus now form. Yeah, this is based on ISO. So I don't create by myself. This is already very long. Okay, so the language is something like this. You can read by yourself. Yeah. So what we have there, yeah, in the what is that called? In the AI prompt is the EPNF. That's why the AI can generate what you want. Okay, so that's the main point there. Yeah, by using this EPNF, yeah, you can ask the AI to do what you want because this is very formal. Yeah. Okay. So the rest of this is just a workshop. Okay, that is in your assignment. Yeah, this workshop is in the assignment. Yeah. Yeah. So I hope you can do this assignment by next week. Yeah, before the midterm, so that you will get better understanding and do the midterm well. Yeah. In the midterm, you have 2 attempts, very lenient. Okay. And 3 hours. Yeah, within these 3 hours, you can do 2 attempts. And the exam is from morning, yeah, until 9 o'clock in the night. So we don't have class next week. Yeah, as we agreed in the beginning of this class. Yeah. So thank you very much. So please read this case study by yourself. Okay. I think it's quite interesting. This is the real super block in Barcelona. Okay. They transform this into a grid system, yeah. A 3 by 3 grids, yeah. And then we can put that into molecule. The same thing, yeah. So at the end, you will have a quite complicated molecule. Yeah. The same thing. This one is the incident report only, the incident response only. I think these are the example that you need to do it. Yeah. That again, if you just want to solve this and then you want to get the assignment done, you just read and then you can get the answer. But the most important is for you to practice, yeah, not just to answer. Okay, you just submit it on time, you get 100. It's not about the grade. Okay? When you practice this, then you will have some ideas, and then you can use this for your group project and eventually for your real project, isn't it? Okay, give me feedback for today's class before we end. What did you learn? Hmm? Yeah. So I just summarize it as this, yeah. So you have atom, your operator, and molecules. Yeah. So remember why we do this, yeah. So it's a new paradigm urban planning, isn't it? Huh? So you want to create a transparency in your policy, yeah. You want to have objectivity, yeah? Very logical policy, quantitative rather than qualitative, and then you have accountability, yeah. It's reproducible, testable, isn't it? Yeah, evidence-based. Okay. And in the near future, okay, I hope we can expand the translation model, and then you can also combine this with AI. Okay. If you want, you can start open source collaboration, you know. And I believe the language itself is not dead, not just this one alone. Yeah. Maybe by building the community together, yeah, we can actually create a better standard later on. Can you see? And you are one of the pioneers because you learned this early. Okay. This is the future of urban planning, you know. Mm. So by doing this, you can share globally, yeah, not just in the Philippines, but you can create global community, yeah, to expand this and learn from each other. Isn't something interesting, you? Okay. Yes. Okay, so thank you very much for today and see you next 2 weeks. In that case, yeah. Yes. Yes, you learn the transport logic, yeah, policy logic, yeah, write it out clearly, yeah. So I hope this is useful, okay. And once you have this atomics, you can put back into the canvas, yeah, and you can ask the website to interpret for you, yeah. This is yeah. So I hope this is useful. Okay, so any other feedback if you want, that's okay. Yeah, so if not, so thank you. So bye-bye. See you in the next 2 weeks, yeah. Next week, you don't have class, but you have exam, yeah, whole day until night.